Okay, Cup. Welcome to the second of the summer pre-course, Interactive Mathematics with Mathematica. Let me bring your attention to the outline. Right. So on Wednesday, I elaborated a little bit about the concept of mathematics as a sort of like a design language or design. Behind everything is mathematics, and you can think of it two ways. You can think of it as organic design being parameterized with mathematics, and it gets manipulated, and then you can do various things with it. Obvious analogy would be you draw little doodles, right? You draw little doodles on a piece of paper, and then you project it to the side of the wall, and you can paint the whole wall with the little doodles. So that's sort of like a one-to-one, okay, magnification. It's a one-to-one correspondence, but it's many times magnification. So you can think of it as a mathematics intervening, in the sense that when you put your doodles into a projector, that's like you embed it in mathematics, and then you apply some kind of multiplier, make it big, right? Now, of course, making it big is only one operation you can do with the projector. But if you did this with a computer, let's say a picture of a baby bear or something like that, and then you parameterize it with set of lines, set of curve, you can actually import it into the computer, and you can manipulate it. You can make the bear bigger, right? But you can also make the bear move, right? So if you can think of mathematics as very powerful in that sense. Now, of course, when I say mathematics being powerful, we mean in modern language, we mean mathematics as calculated by computer. So it's this computational mathematics, right? You need computation, but computation is not achievable without the mathematics behind it. Okay, so and various other things. Now, I also gave you a little bit of sort of like a show and tell, so to speak, of what we could do with Mathematica. I gave you the sort of like understanding of where this pre-course sit, right? It's just like bringing up those of you who haven't, say, done calculus or have been away from formal mathematics for a few years to be on the level with your peers. But at the same time, those of you who have already done linear algebra and calculus, you can start to revisit what you learned, but with a new perspective of what it does in terms of enabling your critical thinking, enabling your design thinking, and enabling your innovative or creative thinking. Okay. And the challenge too is that for those of you who are already doing very well with mathematics, not just for this course, but let's say for next course as well. If you are doing well, the challenge is for you to help your friends, right? And I tell you that I started tutoring very young. Then I was in college. Yeah, I think in college, not before that. I found that tutoring to be a very good experience. Well, I got new friends as well, because students and friends. But more importantly, it kind of crystallized what I learned as I'm forced to elaborate what I learned to the next person, to elaborate the concept. The concept becomes a lot more crystallized, more clearly enunciated for myself. Okay, so that's the sort of the game plan. Okay, that's a game plan. I also mentioned that the idea of a liberal arts education, especially as being envisioned by this institution, this particular Basai program, it's about learning. It's also about lifelong learning. It's about equipping you with ability and inquisitiveness to learn. Okay, and so you're supposed to be greedy, right? Knowledge is power, and you are power hungry. You want to learn as much as you can. It is not your job, or it's not your, from your perspective, you should not be editing what you learn. You shouldn't be filtering what you learn. You shouldn't be telling yourself or asking yourself, do I need to learn this? Do I need to learn that? Do I need to learn this? Do I need to learn that? Okay. You should be hungry and want to learn everything. Now, time is limited, right? Class time is limited. Exercise, homework, all this is kind of a limit constraint on what you can learn. So obviously, mathematics is huge. Every science is huge. It is the instructor, the educator, it's our job actually to do the editing. Okay. So we have to sort of like look through from our experience, from our own understanding of the whole tree of knowledge, and say, okay, given this big tree of knowledge that I have the big picture of, for the students at this time, at this particular moment in time, as a first year, as a second year, as a bachelor, as a graduate student, as a PhD student, what do they need? Okay, so the question of what do I need to learn as a student is not your question. It's actually our question. It's a question for instructor. We have to sort of like think what would be a good tool set, common, sort of like a maybe the greatest common denominator or something like that of the body of knowledge that all the Basai students should learn. Okay, and I've done that with this course, and presumably all the instructors will be doing that throughout. Okay, so whatever cohort, whatever population of students that are here, it's our job, the educator, to basically filter out things that probably could be learned at a later time. Okay, something that could be paced out later, but something that is a little bit more urgent, more critical, would be in here. So you can think of the list as something that has already been gone over by people like me, with a good intention of preparing you for the future. So none of you should be sitting in class with the question, do I need to know this or do I need to know that? It's not always obvious when, why, or how you will need to know certain things. And this was made apparent to me in my own experience. There's a lot of things that I learned when I was an undergraduate. I was happy to learn, because it was fun. But it never, the question didn't arise, when would I need it? But even if I did, if I trusted the educator, my alma mater, at Western Reserve College, case Western Reserve University, to have basically selected the key ingredient. So I learned them all as much as I could, not more. Okay. And a lot of things just came back to me. Some of them came back to me when I was studying PhD. Some of them came back to me when I was working for the Bank of Thailand. Some of them came very late. In fact, before I became a private consultant and start with July here as a formal as a faculty. Was principal data scientist, was also head of quantitative models and enterprise analytics at SCB, and a lot of mathematics came back then. That was ingrained to me much earlier, something like that. Okay, and likewise, a lot of mathematics that I learned when I was at the Bank of Thailand became useful in SCB and all sort of things. Okay, so it's not always apparent when, how, where, why you need this. Okay, but let's just put the question of why do I need to do this aside, and you will enjoy it a lot more. Now, it's also conceivable, okay, it's also conceivable that some of you will graduate Basai and open up a coffee shop and never need to know eigenvector decomposition for the rest of your life. That's also possible, okay? But this class is not just for you, it's for everyone. Okay, so in the good spirit of learning, okay, you should like to try to absorb just as much as is thrown at you, knowing that it's not random. It's by design why we include different items. So So it's deliberate. It's deliberate. Let's put it that way. Okay, that's what course or curriculum design is all about. It's about deliberate selection from the tree of knowledge of what it is we would like to impart to the students so they can graduate as scholars and productive, useful, contributive member of the society. Okay, so with that, what are we doing today? Okay, what are we doing today? So let's look at the outline. They talk about what? Conceptual foundation of mathematics, number, set, logic, equation, function, variable, scales, binary relation, binary operation. A lot of this you will have seen in high school, but you would not have understood them in a more abstract or more generalized concept. Okay, so you probably may have had a thought, but not really investigated why division is actually an inverse operation or something like that can be generalized. Okay, so this is something that we want to get going. Now, I should like for each of you to actually start. You have the Mathematica program, correct? And you have gone to the course view, right? Right, the course view, lecture slides, and you have downloaded these two things at least, right? The mind map, which is this guy right here, and the Mathematica file, which is a copy of my book, my draft textbook, interactive text, chapter 1 and 2, right? Okay, now TA ครับDov and Beton, can you just look at the students, and if anyone press, you have a button that raise your hand or something, or you can just raise your hand. Okay, I think there's a button that raises your hand. Raise your hand right now. Draw attention of your TA if you have not been successful at installing Mathematica. Some of you work off Mac, not PC, right? So you have two different operating systems. I think Kun Surya, the Basic IT, would have arranged for both. Okay, so ก็เป็นตามครับมีใครที่มีปัญหาไหม Anybody raise their hand?
แจ้งครับยังไม่มียกมือครับ
ยังไม่มีนะครับ Okay, good. So I assume that all of you. Okay, so go ahead and start this. So you should have the same screen essentially as I do, right? You should have exactly the same screen as I do now. Okay, so this is it. There's plenty of things to. This is something I'm not using. Okay, so this is just basically we're just for the summer course. Basically, just chapter 1 and 2. It's not really much, really. Okay, but you see this quite rich. So let's get going. Let's get started. Right. Okay, chapter 1. Yeah, chapter 1, number, quantities, set, logics, and uncertainty. So think of the role of mathematics in life. Okay, sounds a little bit silly, but here's a good analogy, by the way. And I don't believe in astrology. I think much of it, if not most of it, is nonsense. But think of the appeal of astrology. Think of the appeal of astrology. You know a whole bunch, many people, you have friends, you have colleagues, right? You are in the process of trying to apply for a job, you're dating, you want to see if this person is the right one for you, blah, blah, blah. Okay? Well, what astrology promises is that if you can represent each individual human being, okay, by some statistics, in particular their date of birth or something like that, their astrology sign, or if they were born in the morning or the evening, or Libra or Cancer or whatever. Okay, you like have an abstract representation of a person. Okay, and then you have an abstract representation of time, like right now, where are we? Are we where are we in the part of the zodiac, whatever? Okay, and you have some kind of calculator. Okay, this calculator is your astrology model. It actually can tell you, okay, it can input, on one hand, the statistics about this guy and statistics about this girl, make some kind of computation. Sorry, I'm not monitoring the students. I don't know if you have questions. So, TA, help me if students have questions, just yell, okay? I'm just kind of like looking at the presentation and not looking at students, okay? So you have this kind of function. You input the statistic that correspond to the date of birth of one person or whatever, and the other input is the date of birth or whatever of the second person. You do some kind of calculation, and that gives you some analytical solution that, okay, these two are a good match, say, okay? And so with that, you can sort of like go back and say, oh, these two persons are actually a good match, or you shouldn't marry this person, or you shouldn't marry that person, something like that. Or maybe you have another function that inputs your date of birth and then input today's date. And the output function would be the probability that you're going to get or lose a job or something like that. So you can see the appeal of astrology. Okay. Now, I believe astrology, the computation itself is rather dubious. A lot of it is just a coincidence. But if you believe them, fine. I don't want to get you all upset. It's early in the morning. But you can see the appeal of astrology, right? It's the idea that you have an extra set of insight that comes from translating physical, in this case, human beings, real empirical object into an abstract expression. You put that abstract expression through some kind of computational rules, and you get some analysis that then gives you insight about the real system. Okay? And that's really the power that abstraction has empowered humanity. Okay? Again, everything else, if you read a little bit about history of anthropology, there's a lot of definition that distinguishes Homo sapien from other species. There's a lot of definition, a lot of attributes that people claim makes us superior or something that is unique to human. Or if it's not unique, it's so developed to the degree that our nearest evolutionary cousins cannot master. Okay, all sort of things. It always comes down to something to do with the ability to abstract. Language is, of course, a way to communicate abstractly, right? Because the word we say right now doesn't mean anything unless we assign a meaning to it. So, with that in mind, the first thing, before we do any kind of calculation, by the way, that's where the word calculus came from, before we do any algebra, well, algebra came from the name of a Muslim scholar in the 13th century, I think. Okay, but before we do any kind of computation, we have to do the first bit. Just like in a computer program, you have to do the input. Well, you have to kind of turn realities into something, into mathematical objects. So today, all we're talking about is about the richness of that numerical or mathematical representation. Okay, how rich is this tapestry? Okay, so obviously, when you think of math, okay, you think of numbers. By the way, I get this all the time because when people know I love math, they would say, I'm not good with numbers. They don't realize that I love mathematics but I'm terrible with numbers. Okay, so numbers is not synonymous with mathematics. Okay, in fact, the reason I love mathematics and not say accounting is because I don't like numbers very much. Now there are mathematicians who love number. They go into number theories and so forth. Okay, not me. I'm quite terrible with numbers. I see a lot of numbers and I have trouble processing. But if I see like a symbolic representation, I'm happy. Okay, so number and mathematics are not synonymous, but it is a starting point. So this is our starting point. Let's start with numbers. Okay, so read this again, and this repeats a little bit of what I said. It's about its ability to perform abstraction and representation that makes us, I guess, superior or outcompete all species or other sentient being. Okay, now let's think of two things that numbers represent. Okay, the most basic things that you do to get numbers. Okay, aside from assigning lucky number, one is counting. It's obvious, isn't it? The other one is measuring. Now keep those two concepts in mind, okay, because they're going to diverge remarkably. Okay, think of counting. 1, 2, 3, 4, 5. Okay, what is required? Just do a little mental critical thinking. Again, a lot of this is to exercise your creative mind and abstract mind. Think about what are you doing when you're counting? First of all, counting only works if you have a concept of sameness. Not exactly the same, but same thing, right? If I want you to count how many female students, right? You definitely have to count 2 different females, but you don't count any male. So the concept of sameness is the sex. It has to be female, otherwise you don't count. It has to be different individual. So right away, there's a concept of classification. Okay? And classification is an agreed upon boundary on your set. Because right now, I'm just saying that I want you to count all your female friends. Then I say, count all your female classmates, right? Or count all your female classmates with short haircuts. And then you have to have the concept of, when exactly is, how long exactly is the hair to be considered haircut and so forth. So there's a lot of implicit abstraction thinking involved. Okay. Now think of measuring. Notice I would not ask you to say, measure the number of friends. Right? Right? So right away, even though they both produce numbers, they actually arise from different operations, from different reality. Counting works if you have a notion of set of female classmate with short haircut. Measuring, on the other hand, has to do with, it's also a numerical thing, right? But it has to do with the extent, the size, how big, how long, how fast, how far. But it is meaningless unless you have a sense of scale, right? And one thing else you might also notice right away, okay, is like counting is based on integer, whereas measuring, it's about divisibility. You can count to the nearest meter, okay, but you never say, how tall are you? Okay, well, I'm 1 meter tall, round this to the nearest meter, or I'm 2 meters tall, round this to the nearest meter, okay? It's always 1.7, 1.6, right? So it's round this to the nearest 10 centimeters, fine. But you never round a human person's height to the nearest meter, okay? It just makes no sense. Because everybody would just be either 2 meters or 1 meter tall, okay? So a lot of this is implicit. Now, so with these numbers, okay, right away, before you do any computation, you can think of conclusion as one computation. It's giving you some insight. It's giving you an answer. Okay, so the activities is counting and measuring, but once you get there, once you get the numbers, what can you do with it? You can do two mental cognition exercise. You can do identification and comparison, all right? You definitely have to identify likes with likes, so you can consider them to be the same set, so you can count them. You can compare. A person who's 1.3 meters tall is shorter than the person who's 1.5 meters tall, whatever, okay? And that's essentially, at the end of the day, what quantitative analytics produces. It produces number, it produces conclusion. Okay? It produces number, it produces conclusion. So this applies for the trivial thing that I mentioned to you, but it also applies to something a lot more meaningful. You know, like the amount of greenhouse gas on average we emit from our lifestyles times number of people, right? Now, so that's all I'm going to talk about numbers, right? So we finish that. Oops. Now, let's talk about binary relation and binary operations. Bi means two, right? Bi means two. Okay? So binary means two part. Relation, what's a relation? Relation means you take two things, okay? Obviously, in this case, because it's binary, right? You take two things and you form some kind of statement. Okay? You can form a kind of statement. Okay, that's a relationship. And that relationship, okay, is what you know about it. Now, in the context of computation, okay, in the context of computation, we allow something else. We allow that relationship to be false. So, in other words, if your notion of relation is you have two persons walking down the street, and you say, oh, the guy is an older brother of the girl. That's a binary relation. Okay. Well, in mathematics or in computation in general, we don't treat this as a truth. We treat this as an assertion, a statement. That assertion could be true, could be false. Okay. So you can think of a binary relation as forming some kind of statement involving two things, A versus B. A something B. A is older than B. A is the father of B. A likes B. And all the statement can be asserted as true or false. Okay, because it could be true. You can say this person is the father, but it turns out not the biological father or whatever. Okay. Or the two people you see walking together, you think they're friends, they just happen to be walking at the same time in the same place. Okay. On the other hand, binary operation or operator is a function. It produces one thing. Okay, it produces one thing. You take two things and you make something else. Okay, you take eggs and butter and you make omelet, whatever. Okay, scrambled eggs. Okay, so you take two things, you don't make a statement, but you produce something else. Okay, so this we call a function, this notion of a function of making something. So with that, let's go through here. Let's see how interesting we can make this. Okay. Right. So let's look at this. Let's look at equality. Now, this is simple to you, right? How many, you couldn't be here if you haven't heard of equality sign. But let's look at this. There are actually two equality signs here. One is a relation. 3 feet is equal to 1 yard, happens to be true. You can say 3 feet is equal to 5 yards. That happens to be false, but it is a relationship. Okay, that equality is considered relationship. Okay, you can assert it. The other time you see this is actually not as a relation, but as an operation. You set something equal to something. Okay, you set the left-hand side equal to the right-hand side. Okay, so what do you actually produce? You take in two things. Again, it's a binary operation, right? You take two things. You take the left-hand side, you take the right-hand side. What do you produce? Well, you still produce left-hand side and right-hand side, except you leave right-hand side the way it was. But you copy the value of the right-hand side and you make the left-hand side equal to that. Okay, so it's actually, you can think of it as taking two objects or taking one object. The right-hand side give it to the left-hand side, but actually you're taking two objects. You're just changing one of them to be the other. Okay, now so click onto an empty space somewhere. Click here. Okay, click here, and just key in something. Just follow my keystroke. Okay, A. Okay, equal to 1. Okay, shift enter. Okay, notice Mathematica say that's my input, that's my output. So input here, this by the way is called shell, a little bit of kernel or whatever sometimes. Okay, this is how by the way, this style of writing is invented by Wolfram or Mathematica. And it was so popular that when the Python language became popular, people developed what's called Jupyter Notebook and follow this protocol, this kind of bracket. So you can say, okay, this is part of this is part of this. You can delete this, but the rest are fine and so forth. So this kind of shell kind of bracketing that you would see later in your Python class in Jupyter Notebook came from Mathematica in the 70s or the 80s. Okay, anyway, so do this. A is equal to 1. Okay, you get this. Now type another one. B is equal to, now type this twice. Okay, 1. Shift enter. What happened there? Okay, I'll tell you what happened. This equality is an assignment. It said A is equal to 1. And this whole expression produces, remember you leave the right-hand side alone, but you do something to the left-hand side. So this produces the value of the left-hand side. This is an operator. This, on the other hand, is a relation, which could be true or false. How come I don't get true or false? Well, the reason I don't get true or false is because Mathematica doesn't know if this is true or this is false. Because it doesn't know what B is. It knows what 1 is. It doesn't know what B is, so it just repeats. Sort of like, say what, that sort of thing, this is your question, just repeat it. Now, let's do this. Let's make B equal to 2. Okay, let's make, go back. Shift enter. Now you get B is equal to 2. Now we can do some kind of assertion. For example, is A equal to B? False. Is A not equal? Okay, not, you put here exclamation mark and equality, and automatically it turns into inequality. It's not equal to B. True. Okay, so right away you see something that you saw so many times in life, but now you see two meanings to it. This is an assertion. Could be true, could be false, because this is a relationship that you claim. I claim that I am your friend. Could be true, could be false. Claim that the two people walking down the street are actually brothers and sisters. They could be cousins. Okay. Equality, on the other hand, is an assignment. I make this equal to that. I make this equal to that. So after I make this, every time I check, it's going to be true because I just made it so, right? I just made it so. So now I know what A and B is, By the way, I want Mathematica to forget. Mathematica to clear things, clear, A and B. Okay. Now notice, by the way, that everything is in black. Okay, it's in black. But once you do clear A and B, the letter turns blue. Blue means something that it doesn't know. In fact, originally when I type in B, you would notice it's equal to, it's blue. Okay, so now if I do this, am I going to get true? No, I'm going to get, repeat back to me because it doesn't know what A is now. So once you clear, it becomes blue. So whenever I type something, it's always blue because Mathematica doesn't have any notion of what it is. Right? So blue now. So you can see why this is blue. So let's get rid of this. So now I don't have definition of AB. By the way, if you're familiar with programming, the word I want to use is that whenever you make inequality, it is a global assignment. In other words, everywhere you go, A is equal to 1. In fact, let's do this again. A is equal to 5. Yeah, now it's equal to 5. I start a new notebook. Okay, and I ask what A is. It's actually 5. So it's actually global as well as universal across session. So once you have a Mathematica session, you make A is equal to 5 here, it's A equal to 5 in every other instance. So it's global and universal across session. Now, if you don't want that, then you can restrict how the definition of A is applied. Okay, we will talk about that later. Likewise, if I clear here, clear A, shift enter, okay, it doesn't produce anything because it's clear. I come over here, and don't save this because I need it, and I ask what is A? It's back A because it doesn't know what it is. So that's easy. So now, okay. So with Mathematica, the formula is designated with double equality. Yeah, okay, so you know that, right? So now we got this. So we can check other thing. Now in Mathematica, function is like the word clear. It's command. Okay, it's you use square bracket. Okay. So if I want something, let's say you want to calculate log of. Okay. Let's say log of 4. Okay, enter. Actually, it sounds like it doesn't know what it's doing. Okay, you want the value, it doesn't give you this. The reason it doesn't give you this is because this is more precise definition. Once you turn into a real number, it loses precision. So Mathematica, it's like in grade school, I don't know if you remember. They always say that, when you do all the multiplication and division, you should do all this crossing, take 2 out from the top, from the bottom, leave the division to the very end and perform that division by calculation once, because that's when you get the rounding error. Okay, if you do all this division in between, you're going to get a lot of rounding error. That's what Mathematica does. It tries to keep everything pure before you make it. Okay, so in this case, the word to get a real value from it is to specify. Okay, so I want to say, I don't want this. I want a real number, and that's preserved for the big N. N of this. Now it gives you this. Notice it gives you 1.38. But if you write this number, okay, by the way, it's got very high precision. Okay. Okay, because it's got this thing notation for implicit. But if you did this, it's going to say false. Right? Okay. Right. Now, let me give you one convention that you will be able to use right away. You can do this. Okay. Some of you may have forgotten what the log function is, but let's say you know what it is, right? But you can do this. Okay. You can do this 2 ways, 3 ways. In fact, you can say log of 4 is exactly the same thing as, there's another shorthand for it, because sometimes you don't want to write left hand bracket, right hand bracket. You say, take the log function, apply it to 4. This will be true. In fact, there's another way of doing it. It's say, take the number 4, pass it to the function log. Oops. Why am I not getting it? Sorry. Wait a second. No, this is, sorry. Oh, sorry. Yeah, it's okay. Oh, maybe okay, I don't know what happened. Okay, let me do this. Oh, I know what happened. Okay, this is what happened. Log of 4 is equal to log of 4 is equal to 4, and do this. The problem before was that I didn't do this. Okay, so what happened is it treats this as one thing. Okay, just a little bit of detail. Now it's good. Okay. So this is called post application. So you can say log of 4 and then take an n. It's the same thing as before, right? Take log, apply it, take 4, apply log to it, apply n to it. It's the same thing as n of log of 4. So key this along with me. It's also the same thing as n applied to log applied to 4. Oops. Okay, so same thing. So all this the same thing. Okay. Except when I did this, I better put a bracket because this post application take what's called the lowest precedence. So it performs everything on the left first. So it's checked if the left hand side is equal to 4. It does this first and then pass it on. That's not what you want. So you want to put this together. So, okay. So key this in your notebook and then save it. You can refer to it later. Okay. So this is a little. Now, why do I make this detour? Because it's very useful. It's very useful. It's like a shorthand. Sometimes you don't want, there's a lot of functions that, you apply function and then function and then exponential and all that. And so there's a lot of bracket. So sometimes this is easier, right? So this is how. So this is called post application. This is of operator notation. Okay. Now in Mathematica, if you put left bracket star and then right bracket and star, this makes a comment. So this is application applied notation. Whereas this one is called its operator notation. Whereas this one, notice anything that's in the star bracket is coming out, so it's in green. So that means it doesn't do anything. It's just for you to look at. So this is for post application. Okay? So, but it's the same thing. I'm going to erase this. So look at it. Now we've talked for good 10 minutes on just inequality. It's something that you had when you were in 3rd grade. Okay? Now let's go back again. How about this? Greater than, less than. Now, can you make this into an assignment operation like equality? No, you cannot. Because you cannot make something less than another thing. Why? Anybody know why I can't make this an assignment operator? Because we don't know how much smaller to make it. So the only thing that mathematics allow is to use this sign as a relationship. Assertion is 7 greater than 3, 4, true. Is 7 less than equal to 4? Okay, notice when you do this, less than equal, it automatically turns into a less than inequality sign. This is going to be false, right? So it is a relation. Okay, so this is some example. Okay, all right. Now, notice what I did here. This is very clever. This is saying I have 2 statements. Both of them true, one of them true. If I do this, either way, that one of them has to be true. So 5 is greater than 4. 5 is greater than 6. That's false, right? That's true. Okay. Okay, that's 5 is greater than 6. That's false. 5 is greater than 6 is false. 5 is greater than 4 is true. Okay. But if all I do is say or, then it is true. Let me see if I can put in more. Okay. So you can put in all kind of things. 7 less 1 is less than minus 1. Okay, all this is nonsense. All this is nonsense. But because there's only one true here, this will return true. But if I did this, and it becomes false. Okay. Now another way of writing this, but I don't want you to worry about it too much, is to say or. This is and. Okay. Now the reason they have this is you can say something like or and 2 greater than 1. What do you think this is going to happen? This is going to evaluate false or true, therefore true, and true, therefore true. Okay, so you can do all kinds of logic. This is the most basic implementation of your analytics. Okay, what do I mean by analytics? Analytics means tools for making analysis. This is what you want to do in life, actually. You're going to say, if this person, okay, this boy height is equal to 1.3. Okay, 1.3. By the way, if I did this, it's going to keep giving the answer, right? So if I want to silence it, I just sort of like put a semicolon. Boy's height is equal to 3. Okay, minimum height. Let's say you're operating amusement park, 1.5. Okay. Boy can write this right and enter this right. Is equal to is the boy's height greater than equal to min height. Let's calculate this. Okay. So what do you think is this value? Okay. Because this is an assertion. This assertion is based on this assignment and this assignment. This comparison, say, is 1.3 greater than equal to 1.5. This is equal to false. You give false to this. This is what you get. And all your business, no matter how mundane your business, how low tech, by the way, you will need this if you graduate from Barca and open a coffee shop. Okay? At the very least, you have to say amount of bill. Amount of bill. Okay? Amount on the bill. Say amount on the tray. Okay? Okay. Let customer leave equal to amount on tray is equal greater than. Okay? What do you think happened? You let this person out your coffee shop? No, you don't. Right? Okay. So believe it or not, what I do in my professional consultancy as principal data scientist, using machine learning, very advanced AI engine, a lot of times comes down to checking something like this. Now, obviously, not that simple. There's a lot of computation here, there's a lot of computation here, but the decision that I give to my client, my client say, I have a problem, please help me solve. Well, what I tend to provide them is this equation, okay? Except there's a lot of things going on here, there's a lot of things going on here, okay? So this can be very complex, But at the end of the day, this is the essence of analytical decision making. Okay. This will be with you for the rest of your Basai and, well, hopefully your career. Okay. It's one form of decision making. There's a lot of, okay. And another thing, another essence is the and, right? So you can say something like this and not thief is equal to true, right? So the person actually paid for the amount that's on the bill, but probably stole something else from the customer. You don't let the person leave. So if not a thief is true, okay, then you can do this. Okay, well, this is false, right? Because the amount is not enough. Now it's true. So the amount on the tray is greater than the amount on the bill and also not a thief. So let this person leave, go on his her merry. Now I should clear this as well, but guess I'm not going to use this. I had to clear A and B.
อาจารย์ครับ
Sorry? Yep, question? Yes.
There are some questions from the chat. The first one is, try this, go to another empty notebook and type. The problem for me was that the style of the text was text and not input. How can we do that?
Okay. Well, normally by default, when you enter something here, it's a sign. Okay, so something like 5 greater than 4 is true. Now, if you did this, by the way, you notice that it allows different types of input. Let me make it big. Okay. There are 1, 2, 3, 4, 5, and something else. Okay, but these are the main type. By default, this is what you get. So 5 is equal to 4 is true. But if you did this, plain text, 5 is greater than 4, enter, nothing. Okay, because you're just typing. Okay, so this is not mathematics. You will notice that the mathematics has a little different font. It's a little bit fatter and it's darker. Okay. Whereas if it's something like this, it's used for text. So that's why you get a text if your input as a plain text. Okay. So either say language input or by default, it should be like that. Now notice here, this is my plain text as well. So I use, this is plain text, this is plain text, this is plain text, this is plain text. This is actually mathematical input. Okay. So hopefully, is that clear? Does that clear the question? By the way, there are, so this is text clear input. Okay. This is a new feature, by the way. This is like, you can, if some of you want to integrate Mathematica with Python, you can do this because you can put Python code. So this is like a Python script. So you actually don't need Jupyter Notebook. This is actually a Jupyter Notebook. So this is a print ยังไงนะมัน P เล็กอีก P ใหญ่ไหม
เล็กครับเล็ก
print เล็กใช่ไหม Hello. Okay, this is a Python. Right. Oops. Oh, I haven't specified that when I use Python. Never mind. Sorry. Okay, so forget this for now. Okay, this is plain text. This is this. Now, these two things are quite interesting. I'm going to talk about it later. Free-form input is an AI way of doing this. So if I didn't know the mathematics, let's say I didn't know mathematics. Okay, I say something like 5 greater than 4. Okay. Or something like that, or you see, it's for some reason it's a bit slow today. So you type in the human language. Unfortunately, it only understands English. You type it, and it's going to try to interpret. So this is like a chatbot, but it doesn't do, general chatbot. It tries to interpret your statement into mathematics. Is this what you want? Yes. If it is, then it's true. Okay. So if you don't know the thing that you want to do, okay, if you know what you're doing, you just do this. If you don't know what, you can guess. So for example, I can do this. This is a mathematical operation, right? But let's say I don't know. I just want to do this. Plot sine between pi and 2 pi. Okay, this is English language. So let's see if we can do that. Is this what you want? Evaluate sine of x. Okay, so this is actually what you would need to do if you knew what you're doing. Okay, so if I know what I'm doing, I would type this thing. Okay, and I get this. Sorry, x. Okay, that's it. Okay, but if I didn't know, I just type in the language. Okay, so let's say plot sine x between minus 2 pi and plus 3/4 pi. Oops. Plot sine. Oh, sorry. I have to do this. I have to say, oh, free form input. Okay. So there it is. So it interprets for you that you want to use the function plot, use the function sine, apply to x ranging from minus pi to plus 4 times. Oh, in this case, it multiplies here. Plus 4 is 4. So that's that, right? So this is a good starter. This is something you can play with. Okay. So if you don't, you can do 2 things, right? If I want to plot sine, I just go to the internet, and I key in Mathematica, okay, plot function, okay. So it's going to be a lot of things. A lot of time, the word is plot, so that's easy. How about sine and cosine function? Sine and cosine. So you click that, it tells you, okay, it takes you to the page. Why was my internet so slow? Okay, that's a sine function. But if you didn't know any better and you don't want to search the internet, you can just, type in using the free form input. Sine of 5 pi. Yeah. The word is sine. So now next time you know how to do this, right? Next time you know how to do this. So you don't have to say this. You just say sine of 5 times pi. Now, pi in Mathematica is actually a symbol. The way you do it is escape. Okay. For special character like pi, see it show up pi. Sine of 5 pi. Okay. It happened to be 0, right? So how about 5.5? Anybody? -1, right? So now you know how to do this. Now I want to plot sine of x. I want to plot, okay, x, right, between, let's say, -5 pi and 5 pi. Okay. So this sine of x plot function takes two things. It has to know what you want to plot, and you have to tell it the rate. So it takes two items. Right? Okay. Just for fun. Would, if I did this, if I put another number 4 here, what's going to happen? It's going to make higher frequency, right? If I make it 0.4, lower frequency, right? You want to play with this? Well, if I want to play with this, I make this something to play with. Play parameter. And I say manipulate this play parameter, play between, what did we use just now? 0.4 and 4. Okay, now you can do this. Right? Let me show you that. So right now the value of play is 1. So set it to equal to 4. Set it to, okay, so you can do this. So you can do this right away. So it's very easy. Okay, so it's quite powerful, and this is what I mean by interactive mathematics. Okay, in a trigonometry textbook, you would see a function, okay, that looks like this, and that's it. That's all you can do. That's all you can do. Maybe there's another plot that shows you this. You say at lower frequency, it's like this. But in my interactive textbook, it's going to be an electronic book. You are going to be able to do this sort of thing. Okay. You can play with other things as well. So times 1 plus another thing, x. Okay, and another, I'm just gonna make it A and B, and B between -4 and 5. I don't know what it's going to look like, okay? But there. I can play with B, I can play with A, I can play with both of them, right? So this is all little silly things that we can play with. We can actually generate design. So you can imagine that, I'm being facetious here. Let's say you design a logo. You design a logo for your company, and you design it like this, right? Let's say it looks like this, okay? And you say, yeah, that looks nice, but I want more wing. Okay, if you do it parametrically, you can do this. Too many wings, take it less. Okay, fine. Okay, you can take this becomes an object. You can manipulate it and turn it into a description, send it to your 3D printer, and you can print spaghetti that looks like this, whatever. I don't know. Yeah, this is I think there's a spaghetti that looks a little bit like that. So that's easy. You can play with that. Okay, so that's a lot of detour from one question. Sorry. So the question was, I put in something and it's not operation, it becomes a text. Well, there are actually 4 different things you can do. Okay.
อาจารย์ครับ another question how can we type this instead of this one
Oh, just do it. No, just do that. Just do that, and then when you type in, it's going to be automatic.
okay
Okay.
Thank
5
you.
less than equal to, see, automatic. It's automatic. Okay. In the older version, it probably isn't, but people say, oh, I want it to be automatic, so it looks nice. So they just keep making it nicer. Okay. Question อีกไหมครับ อันนี้นัดดูในแชทถูกป่ะในอดีตในซูมแชท
okay no more question
no more ครับ
thank you
ครับผมครับ Oops. Okay. I don't need this. Right. So now let's go to addition, subtraction. Now, addition and subtraction to me is the most obvious thing, right? But what's more obvious? Well, we have to think of addition as more obvious than subtracting. Okay. Now, this is where I want you to do a little bit of mental gymnastics. What's the relationship between addition and subtraction? All right. Well, first of all, if you have a young baby brother or sister, you teach him or her addition first. So it's more complicated, right? Subtraction is a little bit more complicated, so you teach him or her later. There's a good reason for that, okay? Why? With addition, you take 2 positive numbers, you always get positive number. With subtraction, you can actually get to negative. And explaining negative number to a baby boy or baby girl is a little bit more difficult. Okay? But that's not what I'm talking about. I'm talking about thinking of addition and subtraction as an inverse of one another. Okay? 5 plus 3. How can you undo this? You undo this by subtracting 3. And you get 5. Okay. So it's not, so I want you to think of this as operation. In fact, let me do this. Instead of saying 5 plus 3, which is how we write it, I'm going to say add 5 and 3. Just to emphasize, this is what we want. Oops, sorry. Plus. Okay? Plus 5 to 3. Now, what's the inverse of this? Is the minus of 3. Subtract. Okay? You get 5. So, is this always the case? Now, I don't know what x is. It's still blue, but it's going to give you this because it doesn't have to know what x is. This is universal. In fact, you can do this. Okay? As long as I use the same thing, it's going to be true. This is universal because this is a forward operation. This is one operation. This is another operation. They are inverse. Not only are they inverse, they are what's called symmetric inverse. In other words, it doesn't matter who you apply it to first. Okay? Right? So, let's ask you a little difficult question. Okay, plus and subtract. Okay, they are inverse. Inverse. Yeah, inverse means it undoes, it undo something. It's meant to undo something. Okay. Yeah. Now, let me ask you a question. Are there operations, not in mathematics, in life, where you have inverse but not symmetric? Okay. Well, I just make it. Okay. Let me do this. One operation, okay, operation one.
อาจารย์ครับ
ครับ
can it be matrix for
Yes,
the inverse
it will
but
be.
not
It will be
symmetric?
matrix. It will be matrix. It will be matrix next Friday. Sorry, I'm taking it slow. Okay, but it will be matrix. It will be matrix. The reason I want to take it slow is because people misunderstand a little bit about how matrix gets applied. It's not a thing about the dimension and what it refers to. Okay, so yeah, it will be. Very good question. Good. Now, this thing about reversibility, I'll just give you a good example. Okay, you're standing on the lake shore, on the shore of the lake. You're facing the lake. Okay, if you walk forward 2 steps and walk backward 2 steps, they seem to be like inverse of one another, right? You end up where you were. But if you take backward step first, you don't get wet. If you take backward step 2 steps and take forward, you end up in the same place, but you're not wet. But if you take forward step first and take backward step, you end up in the same place, but your feet are wet now. Okay, so you can see why symmetry cannot be taken for granted. Reversibility cannot be taken for granted. That's why a lot of mathematicians, they seem to be very tedious about details, because you get exactly something like that with real consequence. You do this, you do A before B, you get back to the same place, but you're not the same as you do B and then A. Okay? And that is life. And that can happen with analytical solution problem as well. Okay, just remember that. Remember that walking forward 2 steps or 1 step, back 1 step, whether or not you're facing the shoreline and you walk into the lake or the pond and then walk back, your feet are wet. But if you walk back first and you walk forward, you still dry. Okay, the inverse operation, but the order doesn't matter. Okay, fine. So addition, subtraction is an operation. It's not an assertion. So there is going to be 2 words here, operation and relation. Multiplication, division, likewise, are inverse of one another. Okay? And, this is a good way of thinking of reading, by the way. Multiplication, in a way, is a humanities computational parallelism. This is what makes your modern life possible. Okay, you may not understand this until you take my, say, machine learning class, but this is what enables your iPhone to recognize your face, or for your camera to do eye detection. Okay, this is what, well, it's not the only thing, it's one of the things that's made everything that you have possible. Well, back when human being invented multiplication, it was also a groundbreaking, it was a game-changing thing, right? Instead of adding 6 bananas, you put them into piles of 2. Okay, and then you add 3 piles. Okay, and then you have an algorithm that tells you that 3 times 2 is equal to 6. Okay, so it's a lot of work. It's a lot of work. Okay, what's much easier between counting 6 bananas or dividing 6 bananas into 3 piles of 2, count the pile, look up the table that says 3 times 2 is equal to 6. Well, obviously counting 6 bananas is much easier, right? But this is where human beings conquered apes. We do the difficult thing. But the difficult thing that we do allows us to multiply gazillion by, whatever, 500 by 500. So just like baby chimpanzee is smarter than a baby human, by the time the human being is 2 years old, we become smarter than babies. Same thing. If you're counting 6 bananas, counting 6 bananas is faster than dividing 6 bananas into 3 piles of 2 or 2 piles of 3 and looking up 6 times 2. But if you develop this more difficult roundabout way, this methodology, you can multiply 734 times 219 bananas, okay, or piles of bananas, okay? You will win, okay, you win. And that's why people with mathematics will always, in the long run, in the bigger problem with a lot more money at stake, people with mathematics will always beat people without mathematics. Yeah, because people with tools will beat people without tools. Unless you restrict yourself to small amount of money, to small bananas, then you don't need the tools. That's why learning tools, learning mathematics is important, because I want you to be smarter than, by the way, chimpanzee can count now, okay? Chimpanzee can count. Okay. They cannot multiply, okay? So up to about 10 bananas, they're probably faster than human beings. But once you get beyond 20 bananas, I think we beat them, okay? So that's why I want to give you the tools. Okay, so human beings beat chimpanzee at counting bananas greater than 20. Likewise, if you're doing big business or whatever, if you're doing advanced innovation, something that's it's going to be innovative, or something that's going to be popular or better than anybody else, you will likely need mathematics. Okay, so mathematics means you can count bananas faster than monkeys. Likewise, people with bananas will always be able to run business better. Sorry, people with mathematics. Okay, fine. Now, we get to what's called properties. And this is where, remember I told you about how tedious we appear to be, right? Very nerdy, why do we care so much about reflexivity, symmetry, asymmetry? Well, just remember that, okay? Walking backward and then walking forward, you still dry. But if you walk forward, you walk backward, you're wet. Your feet are wet. You have to change your shoes, your socks, okay? So think of that in real consequences. So that's why some of these subtleties will become more important. Again, I'm teaching you the tools that looks like an overkill. In fact, that's my secret to business or analytical success. There's a Thai expression saying, you are you're riding an elephant to catch grasshopper. You definitely don't need to ride an elephant to catch grasshopper. But if you learn how to ride an elephant, training yourself on trying to catch a grasshopper, someday you'll be able to catch a lioness, okay? A deer, an antelope, whatever, log trees, because you now have the power tools of elephant. So mathematics is exactly that. All these things will look silly until you run into a lion, okay? So first thing is what's called reflexivity. Reflexivity is a relation. It's asserting X with itself. R is the short term for reflect. For example, this is the property, not of numbers, but property of the relation. So in other words, you check, and this is a function. Now I'm gonna tell you a little bit later about how this is coded. But anyway, all I want you to tell you is that is this relationship less than, greater than, equal? Are they reflexive? Well, this is, by the way, less is this thing, right? Less, greater, yeah, equal. Remember, double equal, not just one equal. Less than equal, greater than equal. Okay. The question is, are they reflexive? If it's reflexive, mean you put in something like 5, 2, and 2. 2 by itself. It's just true. Yeah. It's just true. So I put 2 greater than 2, 2, 2, 2, 2, 2, 2. Now, reflexive means that this is true. Is less than reflexive? No. No. Yes. 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 So let's see if we get that. No. No. Yes. 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 Okay. So if you check the relationship, okay. So this would be something like Bob. Okay. Bob is Bob. Okay. So this is entity. This is entity. This is relationship. Is Bob? This is going to be true. Okay. But something is Bob is father of Bob. Well, at least they have the same name, but we're talking about individual Bob. Okay. Okay. Alice is father of Alice. This is going to be false, right? Okay. Alice is taller or equal height with Alice. This is going to be true. Okay. So that's the basis of comparison. So this is what reflexivity means. You apply it to the same thing. So X with X. Symmetry means you apply with Y. Okay. So these are a little bit of details that maybe in the interest of time, we'll leave it later. So just read this logic. If it's symmetry, means that if X relation with Y is true, then Y is relation X is true. So this would be something like Alice, okay, is sibling with Bob, implies Bob sibling with Alice. So is it symmetric? Yes, it is symmetric. But if Alice is mother of Bob, does it imply that Bob is mother of Alice? No way. No way. Okay? No way. Can I have? Right? And then we have anti-symmetry, which is even stronger. It's saying that if this is true and this is true, then it must be the same. Okay? Transitivity. Transitivity means this relationship, catches on. So, Bob, cousin, with Alice, okay? And Alice, cousin, with Jane, implies Bob, cousin, with Jane. So transitivity, right? But Bob, friend with Alice, and Alice, friend with Jane. Does that imply that Bob is friend with Jane? No. Right? This, by the way, is something that is very important when we do social network analysis. Now, obviously, with social network analysis, we're not dealing with 3 people. We're dealing with hundreds of people. Each of them has different version of relationship. So you can be friend on Facebook, you can be friend, we have a line group, you can have a phone number of each other, okay? And if you are connected on a line group, then if you're in the same group as A as B, B with C, then A and C are in the same group. But if you only have pairwise relationship, then it's not transitive, that sort of thing. Okay. Commutative just means, okay, you take two arguments and you can flip the order. Okay. So for example, A plus B equal to B plus A, true. Okay. Now, how about this? How about A divided by B equal to B divided by A? Well, in this case, it's not always true. It might be true if A and B happen to be the same thing. But if we did this, we put in with real number, 1 divided by 2 is equal to 2 divided by 1. It's going to be false, right? So it's not commutative. So to put in this form, I have something like divide 1 by 2 equal to divide 2 by 1. False, okay? But multiply certainly would work. Oh. You know what? Multiply is product. Okay, sorry, maybe try the word product. Yeah, product. Product is another word for multiply. Oh, that's not true. Yeah, how do you say multiply? Let's go to F1. We use that, and nobody. No. Times. That's another English word. Times. 1 times 2 equal to 2 times 1. True. So that's a little bit confusing. Okay. Multiply in English, it's the same word as product. It's the same word as times. Okay. Or it just happened to be this one. Right. So when in doubt, just put F1. If you click F1, it's going to give you an explanation. Right. So associativity, that means you have 3 things, but you have to do 2 at a time. Okay? Can you do them in different order? Right? Can you do them in different order? In chemistry, I think you have this quite a bit, right? You have 3 ingredients. You have to put A and B together and then C. It would work. But if you put B and C together and then put A, it doesn't work. Okay, so that's associative. Distributivity applies to 2 operations. Well, in this case, there's a lot of details here, but basically something like 5 times 4 plus 2 plus 4 equal to 5 times 2. By the way, in Mathematica, if you because multiplication is used a lot, they just make it a shorthand. So if you make a space, it automatically fills in this multiplication. Okay, you have to put in, if you don't put the space in between, it's 54. If you put a space in between, it knows it's multiplying. Okay, so you don't have to put this sign yourself. It fills in, auto-fills for you. Now, this is where it gets quite interesting. And in fact, this will be a lot more complicated when we get to matrix. The concept above, okay, the concept above of an inverse, okay, it's an inverse, right? What did I say here? I said that this thing undoes the other. Okay, you use subtraction by 3 if you want to undo addition by 3. The point is that this is a vague thing. This is like saying do something and reverse it. A more precise way of saying it is that if you do two things, it's the same thing as doing nothing. Okay, let me say that again. When I was saying that addition and subtraction is an inverse of one another, I would say you do addition by 3, you do subtraction by 3, you get back to the same place. But a more precise way of saying this, is if you do these two things, you're doing nothing. Okay? And in fact, this is what distinguished by addition, subtraction from walking into the lake and walking backward. Because when you walk in the lake, you walk backward, you're not doing nothing, you're doing something. Okay? You're doing something. You only reverse the position, but you don't reverse the wetness. Okay. But the real definition of inverse, is defined by equating it to doing nothing. If you do A and then B, it's the same thing as not doing anything. Then A and B is inverse of one another. Okay? So in that case, you need to define the concept of doing nothing. Okay? Now, doing nothing, how many definitions are there of doing nothing? Well, it depends on what your operation is. If your operation is addition, doing nothing is adding by 0. On the other hand, if your operation is multiplication, then doing nothing is multiplying. Is it by 0? No, it is by 1. So in this case, I define 0 as identity with respect to addition. Because adding 0, that's nothing. If your operation is multiplication, then doing nothing is multiplying by 1. So I define 1 as identity with multiplication. Because multiplying by 1 is the same thing as not producing nothing, not producing 0, okay? But producing the same thing as doing nothing. Producing the same thing as before. Okay? So this is why before I formally talk about inverse, I have to talk about identity. So 0 is the additive identity. Identity with respect to, okay, so it's a bit long with the way of saying identity with respect to addition operation. So it's additive identity. Okay, 1 is multiplicative. So inverse, okay. So inverse is like saying that if you do A and okay, if you add, okay, add. Why do I say that add and subtract is an inverse of one another? Because if you add x by 3 and then you subtract this by 3, it's the same thing as adding 0. Oops. Is it sum? I think it's sum. Oops, not sum. Plus, sorry. There's so many words in English. Okay. Yeah. So this is even cleverer. It's saying that this, okay, it's like checking if x is equal to, oh, sorry. There. Okay. Likewise, let's do a divide and times. Okay. It's the same thing as times x by 1. It's true. Right? So these two are inverse because they produce the same thing as performing with identity. This is a reverse of that because it's the same thing as performing with identity. Okay. So that's what I mean. Now, again, why are we, when you were in grade school, you can say something like 3 times 4 divide by 5, divide by 5, and you get 3. Fine. Why do I have to say something about inverse? Okay. So why do you have to say this and inverse of that? Because it's a multiply, it's the same thing as multiplying by 3. Okay. Why do I have to make a big fuss? Because when we get to this week, okay, multiplying and dividing is not a simple thing. You start with defining the notion of identity. You start the notion of inverse. Then you develop the notion of inverse. Okay? So again, something that looks completely overkill. Yeah, the Kichan Kapakatan really means overkill. Mathematics is about overkilling, but you overkill on simple problem enough time so that you know how to use the tool. So when you get to the big problem, you can use the tools, right? You overkill on 6 bananas because once you have, because a farm full of bananas, you definitely can be can count it faster than chimpanzee. Okay. So this is additive identity, multiplicative identity. Now, today, oops. Okay, today I want to get to the last thing I didn't write here, but this thing is what's called number scale. Now, this is probably one of the easiest concepts in life, but funny enough, even data scientists make mistakes. They make mistakes when they are not mindful of the distinction. So the distinction is easy. But if you don't make that distinction, you can make a lot of mistakes. Okay? It's like, if I ask you to make a distinction between olive oil and corn oil, that's easy, right? But you can imagine that there's a lot of chefs that for some reason are not mindful. So when they're supposed to grab olive oil, they grab corn oil. Now, I don't know if you ever had salad with corn oil. It's terrible. Okay, but with olive oil, it's wonderful, right? It's an easy distinction to make, but it's an easy distinction to ignore. Okay, so this is something that for some reason I'm very good data scientists, who program Python code to do machine learning, they still make silly mistakes like that. That's like chef, just absent-mindedly grabbing a bottle of corn oil, put it in a salad. Okay, it's terrible. Yeah. So this is what I want you to learn. First of all, the first thing you have, okay, What do I mean by number scale? Number scale. Anybody? Are we talking counting? Or are we talking measuring? See, simple concept. I taught you earlier. Very simple, right? You probably thought it was kind of silly to make a distinction. Now you have to go back. We are not counting. We are measuring. This is all about measurement because it's relative to scale. But not so fast. Let's see what happened first. With scale, you can measure something, right? The problem is, I'm going to start you with this thing called nominal scale. This nominal scale is a scale, but you're measuring in the loosest sense of the word. Because normal scale is a simple assignment. All it does is assign Jane is equal to 1. Alice is equal to 2. And Bob is equal to 3. Okay? And all I can do from here is to say that Jane is equal to Bob or not. Is Jane equal to Bob? False. Now, watch this. Watch this carefully. Watch this carefully. I'm going to do this. Is Jane less than Bob? What do you think the computer is going to give you? It's going to give you true. Right? This is where data scientists make silly mistakes. This is meaningless. Because when I assign number 1, 2, and 3, this is my ID number. Okay. If you don't believe me, hey, put your name here, put your student ID here, put your name here, put your student ID here. I mean, put your friend's name, okay? If your ID is 55124 or and your friend is 55107, okay? And let's say this is just an order of you came in, okay? And you want to know if Alice is a better person. Is Alice is a better person than Jane? Okay? Okay? The computer will say yes, but it's meaningless. So when you make this assignment to number, you have to be mindful that it's meaningless beyond this. You are not allowed to use this. The computer will give you the answer. It will be wrong. And in a lot of machine classification problems, people get that wrong in machine learning, simply because of this. They make model based on this, and they make inference based on that. Okay? Wrong, 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 and wrong. And this has happened to professional data scientists, I can tell you. Okay? So the reason I have to say you have to be mindful because the computer, once you assign Jane to 1 and Bob to 2, it's going to treat it as a quantity that you can do all kind of mathematics. It's not going to tell you that, hey, by the way, 1 and 2 doesn't mean anything. It's just an ID, okay? Right? Now, technically, you can get around this by saying Jane equal to 1 and Bob is equal to sine of 2. You can do this. And then you can say Jane equal to Bob. Okay? No. Is Jane greater than Bob? I don't know. Okay? I don't know. In this case, it doesn't mean it doesn't know 1 is greater than 2. It doesn't know if the text value, it doesn't know this. Oops, sorry. It basically doesn't know this. Doesn't know this. Okay. So yeah, you can get around it, but you know, in modeling, sometimes you do get some numerical assignment. So nominal scale just mean, what's the word for nominal? Name. Nominal means name. I named Jane 1, I named Bob 2. It doesn't mean that Jane is less than Bob or Jane is half as big as Bob, or half as tall, or half as smart. Okay, it's just numerical assignment name. The other one is called ordinal scale. Now, in this case, A is equal to 1, and Bob is equal to 2, and okay, let's make this Alice. And then Agatha is equal to 3. In this case, I allow comparison. I allow that 1, because 1 means first is greater than 2 is greater than 3 in this case. Okay, something like this. But normally you wouldn't code it like that, right? You would say something like this would be the winner. The winner gets 3 points. Okay, 2, 1. So is Agatha the winner? Yes. You can do this. But what you cannot do is Agatha minus Alice equal to Jane. Now, the computer will tell you that this is true. Again, this is completely wrong. Because by law or by agreement, ordinal number only gives you order. This is less than this is less than that. But you cannot tell the distance. You cannot do this. You cannot do this. Okay? So it's like a beauty pageant. Okay? You can say that the winner, okay? The winner, the Miss Thailand is more beautiful according to some scale than the runner-up. And the runner-up is more beautiful than the second runner-up. But can you say that, you know, this is the distance. This is so much more beautiful. Or you can say something, can you say something like the Miss Thailand is more beautiful than the runner-up by the same amount or by different amount than that to which the runner-up is more beautiful than the second runner-up. You can't do that because you only have order. You don't have a sense of how far apart or interval. Okay, so you can do ranking and rating. Now, this is not only for scientists to make mistakes. Professional financial risk manager make mistake as well. In investment, there's this thing called investment grading. Okay, so if you say something like, I'll just make it hypothetical. This bond, this investment is rated number A. This one is rated B. This one is rated C. It doesn't mean that A is as far from B as B is as far from C or further, whatever. You can't say it. Just say that A is better than B is better than C. Okay. Now, if you want to make measurement in between, you have to go to the third level, which is interval scale. So now you can make sense. Okay. So Bob is equal to 1.75 centimeter. Jane is equal to 1.72 meter. And Bob is taller than Jane by 3 centimeters. This you can do. Okay, this you can do. So now, what else you can do? You can say something like Thailand, Bangkok is now 60. I'm just making some degree. Chiang Mai now is 63. Okay, so Bangkok now minus Chiang Mai. Okay, oops, it's 2. So it's 2 degrees hotter. The problem is if I do this in Fahrenheit, I did this in Fahrenheit. If I did this in centigrade, okay, so it might make sense. It may not make sense. It depends on the scale because what? Because 0 centigrade, okay, it's the same thing as 32 Fahrenheit. Okay, therefore, there's no absolute 0. So interval scale is like temperature. You can tell the difference. What you cannot do is say something like, is Bangkok now, I use PKK now, okay, divide by Chiang Mai now, okay, let's get some number. Oh, look, Bangkok now is 3% hotter than Chiang Mai. I guarantee you, if you convert the Fahrenheit into centigrade and you do the same number, the same calculation, you will not get the same thing. Let me show you. Okay. So how do I turn centigrade Fahrenheit into centigrade? How do I do that? This is how you turn it into centigrade. Minus 32, right? And then what? Divide by 1.9. Okay. Let's see if this one, let's put the bracket just to be sure. False, right? This is Bangkok in Fahrenheit. This is Chiang Mai in Fahrenheit. This is in centigrade. This is in centigrade. You can't do division. So you can't do ratio. For that, you need ratio scale. And this ratio scale only makes sense if you have absolute 0. Okay, if you have absolute 0. Now, in temperature, there's an absolute 0, but it's not Fahrenheit, it's not centigrade, it is Kelvin. Okay, but definitely something, most of the time you have this. You can say something like Bob is divided by Jane. This is the height, right? Oops. Okay, Bob divided by Jane. Again, I pass it to n because I don't want the ratio. So, but you can do ratio. Bob is actually 1.7% taller than Jane. This we can do. Okay. So just because I make this assignment, okay, the number. So what it means is this. What it means is this. When it comes down to it, number scale is when you assign number to entities, to quality, to attribute. But you only, if the quality that you assign is just an ID, you only allowed to do this. You can do this, you get some result, it be nonsense. If your underlying attribute is rated, like a ranking is ranked, you can do this, you can do this. You can also do this numerically, but you get nonsense. You can do this, you get nonsense. If your underlying is like a temperature thing, you can do this, do this, do this. You can also do this, but this will be nonsense. But if you have something like height, yes. Is the person the same height? You can do that. Is someone taller? Yes. How much taller? Yes. How many percent is that person taller? Okay, so all this you can say with height, you can say it's height 1 equal to height 2. You can do that. Okay. You can also do is greater than. You can also do minus, and you can also do divide. Okay. So you can do all this with anything. Oops. You can do all this with any quantity, but it will only make sense for height. It would not make sense for temperature in centigrade. Okay? Doesn't make sense. So I hope you get that. So that's simple. Right? So, right. So basically, we kind of run right on the mark. Okay. Monday, we go to here. In the meantime, I encourage you to just play. Okay, go to an empty sheet, By the way, once you save, if you don't, I'm not going to save this. Okay. So that I don't have to. So when I start again, it's not going to remember. So it's per session. All the definition is universal per session. So once you turn it off, okay, turn off, okay, then we're done. So that's it. That's what we've got for today. So if you have questions, go ahead and ask. Okay. If not, I'm going to, let's say, call it a day. Not your TA. Okay, I'm gonna have a Pinat Kongkan is like a master TA. He's been my TA for, oh yeah, just save as. Okay. But what you might not want to do is save the on top. You just put in a second file so you can play around with it. Okay, just save as. And so I'm gonna have a younger guys which is a graduate, fourth year. So pick up and P Petong. P Petong is the one recording. And pick up. Can you show your face a little bit? Huh? So anyway, yeah. This one is pick up, and this is P Petong and Pinat. Okay. Pinat will definitely be my TA for a more advanced class, like for machine learning and data analytics. Okay. But they actually all working for my consultancy project with UOB Asset Management. Good. Kongkan Pinat has been with me for a long time. He was in my team at SCB. He was in fact a senior data scientist. Okay, so with that, I'm going to sign off because I do have another meeting. So play with it, and feel free to communicate with each other. You know, on if you have this small question you want to ask your friend or something, just ask it in the line group. Chances are it's going to benefit everyone. So make you even though you just need to ask one person, you should ask this. Can we watch? Yes, we can. Okay, P Petong is going to make a recording. In fact, he recorded the last session. I'll make it available, I think, on YouTube, because that saves the space. At some time this weekend, I'll let P Petong record this session first, so we have two, and then I'll make the link or available on Course Bill or inline. Okay, doke. So with that, good luck, everyone. ครับผม Okay, I'll see you on Monday. สวัสดีจ้ะ